What is the color of the ocean? Well, the answer varies depending on who you ask. An ancient Greek would answer, wine dark, while some Aboriginal people in Australia will say it's black. Russians may change their answers from time to time. Physically speaking, color is nothing more than a frequency of the light waves. The lowest visible frequency of light is called red, and the highest frequency we can detect is referred to as purple. Between the boundaries of infrared and ultraviolet, a spectrum of various light wavelengths exists, including blue, green, and yellow. The sun emits all colors of light, but things around us reflect only a part of them. For example, a banana looks yellow because it only reflects yellow light. The other colors are absorbed by the object, and the light energy is turned into heat energy. This is how color scientifically works. However, color is more than just a physical phenomenon for Homo sapiens. We give names to different wavelengths of light, perceive them through our cultural filters, and enjoy various combinations of them as forms of artistic expression. What is the color for humanity? The sensation of color is produced in the brain, not the eye, and the brain does not take the signals from the retina at face value. It is constantly engaged in highly complex and sophisticated computation to stabilize our perception under different lighting conditions. From an evolutionary perspective, if the same fruit on a tree looked one color at noon and a different color in the evening, it would be troublesome because color would not be reliable information to tell if it's ripe or not. When the signals from the retina do not correspond to what is expected, the brain adjusts them and makes us see a color that does not exist, based on our past experiences and memory. For example, a study shows that a perfectly gray picture of a banana can appear slightly yellow to us, since the brain remembers bananas as yellow, and thus regulates the sensation towards its expectation. Languages also significantly interfere with our perception of colors. Russian has two distinct color names for the range that English covers under the name blue. They call light blue, голубой, and dark blue, синий. Just as we differentiate red and purple as different colors, Russian speakers distinguish light blue and dark blue as separate categories. When they are tested to tell the difference between two shades of blue, Russian speakers showed quicker responses than English speakers across the boundary between голубой and синий. Our color perception is largely influenced by our memory, culture, language, and so on. It's impossible to perceive colors purely without any bias. Homer is an ancient Greek poet, known as the author of the epic poems Iliad and Odyssey, which beautifully portray adventures of Greek gods and heroes. Despite his vibrant depiction, his works contain a lot of color descriptions that are puzzling to us today. For example, he described the ocean as wine dark. He also applied the term wine dark to cattle. How is it even possible that the sea and cattle have the same color as wine? This is not because Homer was colorblind, but because ancient Greek didn't have a word meaning blue. Nothing has changed in the eye's anatomy over the last millennia, but languages are constantly changing. For example, the native population in Murray Island speak their unique language. Until recently, they only had 3 distinct names for colors: black, white, and red. Everything other than red was probably categorized into black or white, based on its brightness, which is why they called the sky and the sea black. Anthropologists have shown that any language acquires the names for colors in a particular order. Languages start with black and white. Red is always the second color to receive a name. Then, languages discover yellow and green, and finally a word meaning blue is coined. People give names to things they feel the need to talk about. Red is a signal for many vital things, such as bleeding and face flushing due to fever. Yellow and green are also important to spot ripe fruits from a green background. Of course, blue is familiar as the color of the sky and the sea. But ancient Greeks and many others didn't find any pressing incentives to name it. Everything you see on a screen is actually a combination of the three primary colors, red, green, and blue, or RGB. Surprisingly, our biological color perception works the same way. We have a thin layer of cells in the back of our eyeballs, called the retina. The retina has two different types of light-detecting cells, rods and cones. The rods are used in low-light conditions to detect brightness, and cones are used to perceive colors. There are three kinds of cones, each of which roughly corresponds to the color of red, green, and blue. When we see a color, each cone sends its own distinct signal to our brain. For example, when we see purple, both the red and blue cones get activated. Our brain receives the signals from the cones and processes this information to reconstruct purple. Everything we perceive through the eyes derives from the combination of red, blue, and green. Three primary colors, when carefully arranged on a canvas, creates breathtaking vibrance and harmony in the arts. For example, the Madonna della Sedia serves as a prime example. While the red color of Madonna's sleeve at the center tightens the overall impression, the green on the left, and yellow and blue on the right, whose mixture creates green, provide a sense of balance. Another work showcasing a skillful combination of primary colors is Fine Wind, Clear Morning, by Hokusai, part of his 36 Views of Mount Fuji series, which is characterized by the dynamic contrast of the red mountain, the blue sky, and green forests. Café Terrace at Night, by Vincent van Gogh. It fascinates us at the very first glance, perhaps because of his elaborate use of colors. The striking contrast between the vivid yellow and deep blue immediately draws our attention. Whether Van Gogh intended it or not, the allure of this painting can be explained by the theory of complementary colors. Complementary colors are pairs of colors located on opposite sides of the color circle, such as blue and yellow, green and magenta in the RGB model. When they are placed next to each other, they create a strong contrast yet beautiful harmony. Another intriguing aspect of complementary colors is that, when they are mixed, they produce gray color by killing each other's tones. Along with the tones, brightness of the colors have to be in contrast. Vibrant yellow calls for dark blue to neutralize its intensity and maintain balance. As a result, a pair of complementary colors can create a distinct harmony that entirely differs from one with similar colors. It is an equilibrium within a dynamism, unity within a diversity. Some of the masterpieces in the history of the arts take great advantage of complementary colors. Girl with a Pearl Earring by Johannes Vermeer is characterized by the combination of yellow and blue. While Van Gogh's work places bright yellow against dark blue, Vermeer harmonizes intense blue with dull yellow. Impression, Sunrise, by Claude Monet also makes a textbook example, which features the vivid red sun against a grayish cyan background.